Welcome to this session where we'll explore LeetCode problem number 1240, tiling a rectangle with the fewest squares. In this problem, we aim to find the minimum number of squares required to completely tile a given rectangle of size nxm. Let's dive into the details and approaches to solve this interesting challenge. In this problem, you are tasked with tiling a rectangle of size nxm using the fewest number of squares possible. Here, a square is defined as a smaller rectangle with equal width and height. The goal is to determine the minimum number of such squares needed to completely cover the rectangle without any overlaps or gaps. For input, you will be given two integers, n and m, which represent the height and width of the rectangle, respectively. Both dimensions are constrained between 1 and 13, inclusive. The output should be a single integer representing the minimum number of squares required to tile the rectangle. To better understand the problem, let's look at some examples. In the first example, the rectangle has dimensions n equals 2 and m equals 3. The output is 3, meaning the rectangle can be tiled using 3 squares. One possible arrangement is to use 1 2x2 square and 2 1x1 squares. This configuration covers the entire 2x3 rectangle with no overlaps and uses the minimum number of squares. In another example, where n equals 5 and m equals 8, the output is 5. This means the 5x8 rectangle can be tiled with 5 squares in total. For the rectangle with dimensions 5x8, one possible arrangement is to use 3 3x3 squares and 2 2x2 squares. This adds up to 5 squares, which is the minimum required to completely cover the rectangle. In the next example, with n equals 11 and m equals 13, the output is 6, meaning 6 squares are sufficient to tile the rectangle. Here, the solution involves using a combination of squares with various dimensions to achieve the optimal result, ensuring that the total number of squares remains as low as possible. When solving this problem, note the constraints: both n and m are positive integers between 1 and 13. This means the solution must account for edge cases. For example, if one dimension is 1, like 1x13, the rectangle can only be tiled using n m1x1 squares. If both dimensions are equal, such as 13x13, the rectangle is already a square, so only one square is needed. For smaller dimensions, like 1x1 or 2x2, the solution is straightforward. The challenge lies in finding the most efficient tiling for larger rectangles. Given the constraints, dynamic programming or backtracking approaches are well suited for efficiently determining the optimal solution. These strategies allow us to balance computational efficiency with the need to minimize the number of squares used. To solve the problem of tiling a rectangle with the fewest squares, we first need to understand the different approaches available. One option is the brute force approach. The intuition here is to try every possible way to tile the rectangle, placing the largest square that fits at each step and then recursively solving the remaining area. This involves exploring all permutations of square placements, which makes the implementation heavily reliant on recursion and backtracking. However, the time complexity of this approach is extremely high since the number of states grows exponentially, making it impractical for larger rectangles. Another option is dynamic programming, where we use a table to represent the minimum number of squares required to tile a rectangle of size n by m. By breaking the problem into subproblems and reusing previously computed results, we can significantly reduce redundant calculations. The implementation involves iterating over all possible square sizes for a given rectangle and minimizing the total number of squares through recursive calculations. While this is more efficient than brute force, the time complexity remains relatively high, and the approach requires considerable memory for storing intermediate results. Additionally, there's the greedy approach with optimization. Here, the main idea is to always place the largest square that fits within the current rectangle. By doing so, the problem size is reduced quickly. To further refine the process, pruning techniques are applied to avoid exploring invalid or suboptimal states. The implementation combines backtracking with this greedy strategy, prioritizing the placement of the largest square at each step while recursively solving the remaining uncovered area. The time complexity is improved compared to brute force, as pruning significantly narrows down the search space. However, the greedy approach alone does not always guarantee an optimal solution. When enhanced with backtracking and pruning, it becomes much more competitive, blending heuristic placement with exhaustive search to achieve better results. This makes it an appealing alternative for tiling problems, especially when computational resources are a concern. The chosen strategy combines the greedy approach with backtracking. By placing the largest possible square first, the greedy method effectively shrinks the problem size. Backtracking, in turn, ensures that all potential solutions are explored, allowing us to identify the optimal one. Pruning rules play a critical role in this method by eliminating states that are clearly non-optimal or exceed the current minimum square count. A key observation here is that the complexity of the problem arises from the vast number of ways the rectangle can be divided. By prioritizing larger squares and applying pruning, we can significantly reduce the number of states to explore. The real breakthrough is the realization that combining these two methods provides an ideal balance between efficiency and accuracy. The implementation involves recursive placement of squares, starting with the largest size, and using backtracking to minimize the total square count. This approach, while not polynomial, proves to be efficient for moderate rectangle sizes, making it both practical and effective. Each approach has its own trade-offs. The brute force method guarantees that all possibilities are explored but is computationally infeasible for large inputs due to its exponential time complexity. Dynamic programming improves performance with memoization but still demands extensive memory and computational resources, especially for larger rectangles. The greedy approach with optimization strikes a balance between efficiency and accuracy by using heuristic methods to place squares and backtracking to explore other possible configurations. This combination allows the search space to be narrowed while still finding optimal or near-optimal solutions. The chosen strategy leverages the strengths of both greedy and backtracking techniques. It is practical for moderate rectangle sizes, achieving optimal results in most cases while being significantly faster than brute force. Although it may not be the fastest solution for very large inputs, it offers a well-rounded and efficient approach for solving this tiling challenge. The problem we're tackling here is to tile a rectangle of dimensions n by m using the fewest number of squares. Each square must have an integer side length, and they must fit perfectly without any overlaps or gaps. The challenge lies in finding the optimal arrangement of these squares to minimize their total count. To solve this, we employ a backtracking approach with pruning to systematically explore possible configurations while cutting off paths that are unlikely to lead to an optimal solution. First, we represent the tiling process using a 2D grid of size n by m. To simplify the computation, we reduce this grid to a 1D array called heights, where each element tracks how high the tiles have been stacked in each column. The objective is to ensure all columns reach the target height of n, using the minimum number of squares. The algorithm terminates when all entries in the heights array equal n, at which point the rectangle is fully tiled, and we return the number of squares used in this configuration. The next step involves recursive backtracking. We identify the first column with the smallest height, referred to as min_col, as the starting point for placing the next square. Then, we determine the largest possible square size, k, that can fit starting from this column. The size k is constrained by two factors, the remaining height in min_col and the number of adjacent columns that also meet the height requirement. For each possible square size, starting from the largest, we attempt to place the square at min_col. This requires updating the heights array to reflect the new placement. From here, we recursively solve the subproblem with the updated heights configuration. After exploring this path, we backtrack by undoing the placement to test other configurations. Pruning is a critical part of this process. If the current number of squares exceeds the best solution found so far, we terminate this branch of exploration. Similarly, if a square violates constraints or cannot fit, we skip to the next size. To optimize further, we prioritize starting with the largest square size, as this reduces the depth of recursion. Additionally, we use memoization to cache and reuse results for previously encountered heights configurations, avoiding redundant calculations. This approach is powered by several key insights. First, placing the largest square available often leads to faster convergence because it minimizes the remaining open area that needs to be tiled. Second, representing the tiling state with a 1D heights array is a significant simplification compared to working directly with a 2D grid. It reduces the problem's dimensionality, making it more manageable. Pruning plays a pivotal role in limiting the search space, as we stop exploring paths that are already worse than the best solution found so far. To support the algorithm, we rely on two main data structures. The heights array tracks the current height of tiles in each column, reducing the problem size from n by m to just m. The memoization table stores results for previously seen heights configurations, ensuring we don't repeat computations unnecessarily. Regarding complexity, the time required depends on the rectangle's dimensions and how effectively pruning reduces the search tree. The space complexity mainly arises from the memoization table, which grows with the number of unique heights configurations encountered during the process. Finally, let's consider some edge cases that the algorithm must handle efficiently. Small rectangles, such as 1 by 1 or 1xn, are straightforward to solve since they require either one square or a series of stacked tiles. For large squares where n equals m, the solution is always a single square, making these cases trivial. However, highly uneven dimensions, such as 1 by 1000, introduce a unique challenge. These scenarios require the algorithm to efficiently handle a large number of smaller tiles, emphasizing the importance of pruning and memoization to keep the computation feasible. By addressing these edge cases effectively, the algorithm ensures robustness across a wide range of inputs, from simple to highly complex configurations. Here, we begin implementing the solution by defining a class called solution with a method tiling rectangle that takes two parameters, n and m, representing the dimensions of the rectangle. To start, we initialize a grid of size n by m filled with zeros, which will help us track the placement of squares. We also define a variable min_squares to store the minimum number of squares needed, initially set to infinity as we aim to find the smallest possible value. Next, we define a backtracking function that takes placed_squares as an argument to keep track of how many squares we've placed so far. Inside this function, we first check if the current number of placed squares is already greater than or equal to min_squares. If so, we return early, as there's no point in continuing. Then, we locate the first empty cell in the grid by iterating through its rows and columns. If no empty cells are found, it means the rectangle is completely covered, so we update min_squares with the current count of placed squares and return. After finding an empty cell, we calculate the maximum possible size of a square we can place starting at this position, which is the smaller of the remaining rows or columns. We then attempt to place squares of decreasing sizes at this position, starting from the largest possible size. For each square size, we first check if it can be placed at the current position using a helper function canPlace. This function iterates over all cells within the bounds of the square and checks if any of them are already occupied. If placement is valid, we proceed to place the square using another helper function placeSquare, which modifies the grid to mark the cells covered by the square. After placing the square, we recursively call the backtracking function with an increment count of placed squares. Once we've explored all possibilities for this configuration, we remove the square by calling placeSquare again, but this time with a value of 0 to reset the grid cells. The canPlace function ensures that only valid placements are allowed, while placeSquare handles both adding and removing squares by toggling the grid cells between 1 and 0. Finally, we kick off the backtracking process by calling it with an initial count of 0 placed squares. Once the recursion completes, we return the minimum number of squares found, which is stored in min_squares. Here, we begin by defining a solution class that uses a backtracking approach to solve the problem of tiling a rectangle with the fewest squares. The grid array represents the rectangle, initialized with zeros to indicate empty cells. The variable min_squares keeps track of the minimum number of squares used so far. The main method, tiling rectangle, takes the dimensions of the rectangle, n and m, initializes the grid, and starts the backtracking process. The backtrack method is where the recursive exploration happens. It takes the current count of placed squares and the rectangle dimensions as parameters. If the current count of placed squares exceeds or equals the minimum found so far, the method stops further exploration to save computation time. Then, it searches for the first empty cell in the grid by iterating row by row and column by column. Once it finds an empty cell, it records its position to determine where to place the next square. Now, if no empty cell is found, it means the entire rectangle is covered, so we update the min_squares value with the smaller of its current value and the number of squares used. Otherwise, we calculate the maximum possible size for a square that can start at the current empty cell. This size is limited by the remaining rows and columns in the grid. We then iterate from the largest square size down to 1, attempting to place a square of each size at the current position. Before placing a square, we use the helper method canPlace to check if the square fits in the grid without overlapping any already filled cells. If it's valid, we temporarily place the square using the placeSquare method, increment the count of placed squares, and recursively call backtrack to continue tiling the rectangle. After finishing the recursive call, we backtrack by removing the square, restoring the grid to its previous state, and continue the loop to try smaller square sizes. The canPlace method checks if a square of a given size can be placed at a specific grid position. It iterates through the cells that the square would occupy, ensuring that all are empty. If any cell is already filled, the method returns false. If all checks pass, it returns true. The placeSquare method is then used to either place or remove a square from the grid. It takes the top left corner of the square, its size, and a value indicating whether to add or remove the square. By iterating over the cells in the squares region, it updates the grid, setting the cells to the given value 1 to mark them as filled or 0 to mark them as empty. This helper method is essential for both placing squares during recursive exploration and undoing changes during backtracking. Together, these methods form the core of the backtracking solution, enabling us to efficiently explore all possible tiling configurations. In this example, we are tasked with tiling a 2x3 rectangle using the fewest number of squares. To begin, we initialize a grid as a 2x3 matrix filled with zeros, which represents our empty rectangle. Additionally, we set a variable, min_squares, to infinity to keep track of the smallest number of squares we can use. The backtracking process begins by identifying the first empty cell at position 0, 0, where we attempt to place squares. The largest square that can fit in this rectangle at 0, 0 is a 2x2 square, as it's limited by the dimensions of the grid. When a 2x2 square is placed, the grid updates to show that the top left and adjacent cells are now filled, and we can proceed to explore further placements. With the 2x2 square placed, we increment the count of placed_squares to 1 and continue to fill the remaining empty cells. At position 0, 2, we attempt to place a 1x1 square, which fits perfectly. The grid updates to reflect this placement, and the count of placed_squares increases to 2. Next, we move to the final empty cell at 1, 2, where another 1x1 square is placed, completing the tiling of the rectangle. This update to the grid shows that all cells are filled, and the total count of squares used is now 3. Since all cells are covered, this configuration represents a valid solution, and we update min_squares to 3, as it is the fewest number of squares used so far. To ensure we explore all possible configurations, the algorithm performs backtracking to try alternative placements. However, after checking all configurations, we find that the minimum number of squares required to tile the 2x3 rectangle remains 3. Moving on to a larger rectangle, we consider a 3x5 grid. Here, we initialize a 3x5 grid filled with zeros and set min_squares to infinity. Once again, we start the backtracking process at the first empty cell, which is at 0, 0, and begin evaluating the placement of squares. The goal remains to cover the rectangle using the fewest number of squares. The first placement we try in the 3x5 rectangle is a 3x3 square at position 0, 0. This is the largest square that fits at this position. After placing it, the grid updates to show that the top left section is now filled, and placed_squares becomes 1. Next, we move to the top right portion of the grid, where we attempt to place a 2x2 square at position 0, 3. This placement fills most of the remaining empty cells in the top 2 rows, and the grid updates accordingly. With 2 squares placed so far, the remaining empty cells are in the bottom right corner, where we can place 2 1x1 squares to cover positions 2, 3, and 2, 4. After placing the 2 1x1 squares at 2, 3, and 2, 4, the grid is completely filled, and the total count of placed_squares reaches 4. Since all cells are covered, this configuration represents a valid solution. We update min_squares to 4, as it is the fewest number of squares used to tile the 3x5 rectangle. Finally, we consider the case of tiling a 4x4 rectangle, which is a square. The process begins by initializing a 4x4 grid filled with zeros. As before, we aim to minimize the number of squares used to completely cover the grid. In the case of the 4x4 rectangle, the simplest solution is to place a single 4x4 square, which fills the entire grid in one step. This placement results in a grid where all cells are filled, and the total number of squares used is just 1. Since no smaller number of squares can be used to cover the rectangle, the minimum number of squares required is 1. This demonstrates that for square grids, the optimal solution is always a single square that matches the dimensions of the grid. To analyze the time complexity of this solution, we start by examining the behavior of the recursive backtracking approach. The algorithm explores every possible way to tile the rectangle with squares, and the depth of recursion can extend up to O and *m in the worst case. This is because each recursive call corresponds to placing one square, and the rectangle contains at most n*m cells. For every recursive call, the algorithm tries to place squares of all possible sizes, starting from the largest square that can fit, down to a square of size 1. This involves O, min, n, m iterations, where n and m are the rectangle's dimensions. Additionally, for each square placement, the canPlace function checks whether the square fits into the grid by verifying all cells within that square, which takes O, size ⁻2, time. Combining these factors, the overall search space is exponential, as the algorithm evaluates all valid configurations of square placements. This combinatorial growth explains why the time complexity is so high. The worst-case time complexity occurs when the algorithm exhaustively explores all possible configurations of square placements. The total number of recursive calls, in this scenario, is exponential due to the vast number of combinations to evaluate. For each call, the algorithm performs up to O, min, n, m iterations for square sizes, and each iteration involves O, size ⁻2, operations for the canPlace check. As a result, the worst-case time complexity can be expressed as approximately O, min, n, m, and *m. While this represents an upper bound, it's important to note that pruning optimizations significantly reduce the search space in practice. For instance, the algorithm abandons paths where the number of placed squares exceeds the best solution found so far, which helps mitigate the exponential growth to some extent. In terms of space complexity, the algorithm's requirements are determined by two main factors: the storage for the grid and the recursion stack used during backtracking. The grid is represented as a 2D list of size n*m, which directly translates to O and *m space. The recursion stack, on the other hand, grows with the depth of the backtracking calls. In the worst case, where each cell is covered by an individual square, the depth of the recursion stack can also reach O and *m. When you add these two components together, the total space complexity becomes O and *m for the grid plus O and *m for the recursion stack, giving us a final space complexity of O and *m. This means the algorithm's memory usage scales linearly with the size of the rectangle. To better understand the efficiency of this solution, let's compare it to a brute force approach. A naive brute force method would attempt to generate all possible ways to tile the rectangle and then determine which configuration uses the fewest squares. This approach results in an even larger search space because it lacks any optimization strategies, making it computationally infeasible for larger grids. In contrast, the backtracking approach used here introduces significant optimizations. By leveraging pruning, the algorithm abandons paths where the number of placed squares is already worse than the best solution found so far. Additionally, it prioritizes placing larger squares first, which tends to cover more area and reduce the number of recursive calls. Despite these improvements, the problem's exponential nature remains, meaning the time complexity is still heavily influenced by the size of the search space. The time complexity can vary significantly depending on the specific dimensions of the rectangle. In the best case, such as when the rectangle is already a perfect square, the algorithm quickly determines the solution and terminates. Here, the time complexity is minimal, roughly O and *m, accounting for grid initialization and a few recursive calls. In the average case, where the rectangle has arbitrary dimensions, the number of recursive calls and the resulting time complexity depend on the complexity of the search space, which is typically exponential. The worst case arises when the dimensions of the rectangle lead to a highly complex search space, such as when n and m are large and do not share common factors. In this scenario, the time complexity can reach O, min, n, m, and *m. This exponential growth is inherent to the problem, as the algorithm must explore various combinations of square placements to ensure the optimal solution is found. Even with pruning, the sheer number of configurations makes the worst-case behavior computationally expensive. When solving this problem, there are several common mistakes to watch out for. First, many solutions overlook the symmetry in rectangles. A rectangle with dimensions nxm is equivalent to one with dimensions mxn. If this symmetry is ignored, it can result in redundant computations and inefficiencies. To avoid this, always sort the input dimensions so that the smaller value is treated as the height. This simplifies the logic and reduces unnecessary calculations. Next, it's important to focus on placing the largest possible square first. Some solutions mistakenly try smaller squares, like 1x1, early on, which leads to deeper recursion trees and more computational overhead. Placing the largest square first ensures you cover more area in fewer steps. Another mistake is failing to prune the search space effectively. If the current number of squares in your solution exceeds the known minimum, you should terminate that branch of recursion immediately. Without this type of pruning, your algorithm may waste time exploring unproductive paths. Finally, inefficient memoization strategies can also slow you down. For instance, if you don't memorize results for rotated rectangles, the same subproblem might be solved multiple times. Using a robust memoization approach ensures that repeated calculations are avoided, saving both time and resources. Another common pitfall is relying on hard-coded edge cases. For example, some solutions might include specific logic for cases like n equals 11 and m equals 13. While this may work for those inputs, it undermines the generality of your algorithm. Instead, strive for a dynamic solution that can handle all valid inputs without requiring special cases. A key insight for this problem is that it revolves around exploring combinations of squares to minimize their count while completely covering the rectangle. Depth-first search with backtracking is a natural fit for this type of problem because it allows an exhaustive search of all possibilities. However, combining it with memoization is essential to make the process efficient. Recognizing patterns is also important. This problem shares similarities with other algorithmic challenges, such as partitioning or knapsack problems, where the goal is to allocate resources optimally while minimizing redundancy. In interviews, it's helpful to discuss the trade-offs between brute force approaches, which are slower but guarantee correctness, and heuristic-based methods, which may be faster but don't always yield the best result. Additionally, be prepared to explain the complexity of your approach. Backtracking alone has exponential time complexity in the worst case, so you should highlight how pruning and memoization can significantly reduce computational overhead. This problem is closely related to several other dynamic programming challenges. For instance, LeetCode 1000, minimum cost to merge stones, involves minimizing the cost of merging items, which is conceptually similar to minimizing tiles in a rectangle. Another example is LeetCode 312, burst balloons, a problem that focuses on optimal subproblem division to maximize or minimize results. LeetCode 1547, minimum cost to cut a stick, is another great comparison. It involves dividing a structure into smaller pieces while minimizing cost. Finally, LeetCode 174, dungeon game, is relevant because it also relies on efficient state representation and making optimal decisions at each step. When considering alternative approaches to this problem, one option is to use a greedy algorithm. This involves always placing the largest possible square first. While this approach is fast and efficient for some inputs, it doesn't guarantee the minimum number of squares. This trade-off makes it less reliable for cases where optimality is required. Another powerful approach is dynamic programming. Here, you can construct a DP table where dp, I, j, represents the minimum number of squares required to tile a rectangle of size ixj. This method avoids redundant calculations by solving subproblems only once and reusing the results. However, it can be memory-intensive, especially for larger rectangles. Finally, depth-first search with backtracking and memoization is a robust approach. By recursively exploring all possible placements of squares and storing results for subproblems, you can guarantee optimality. The trade-off is that this method has an exponential time complexity in the worst case, but with proper pruning, such as stopping when a branch exceeds the current minimum, it becomes far more efficient. Together, these techniques offer a range of options depending on the constraints and requirements of the problem. Thank you for joining the walkthrough of problem number 1240. Tiling a rectangle with the fewest squares. Today, we summarized the problem, explored the solution approach, and discussed its key concepts and takeaways. If you enjoyed this session, please like, subscribe, and share to support the channel. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!